External flows are flows over bodies immersed in an unbounded fluid so that the flow boundary layer can flow freely in one direction. Along with flow, there's also drag. There's form drag or pressure drag, and then from velocity gradients near the sphere or whatever body that's falling through air or water, there is viscous drag or friction drag. The sum of the two is the total drag force. Also, at different Reynolds numbers, there are different phenomena that occur. As you can see on the slide, there's creeping flow or Reynolds number less than 1, where friction drag dominates and the boundary layer is laminar and wraps around the object without separating. At a Reynolds number of about 2000, there's a stagnation point and wake point, and then you can see from then on how the fluid will flow. Another thing that also occurs is that roughness makes flow turbulent at a lower Reynolds number, which influences the design of things like sports uniforms, cars, etc. And there's also momentum balances that can be done. If you have, per se, a ball falling with the y direction positive as down, you can do the force drag equals the weight force minus the buoyant force and solve for either of these three components. One of the concept questions along with this video is who goes faster, a heavier or a lighter skydiver? There are two forces acting on the skydiver, the gravity and drag force, ignoring the buoyant force. The downward force of gravity stays the same despite the velocity of the person. However, as the relative velocity increases, the magnitude of the drag force also increases until it is equal to the gravitational force. At this point, there is no acceleration and the person has reached their terminal velocity. Since the drag force is proportional to speed, a heavier skydiver must go faster for the drag force to equal their weight. My second concept question to go along with this video is, does a golf ball with or without dimples go faster? The answer is, the golf ball with dimples will go faster because roughness can decrease the drag coefficient. Roughness makes flow turbulent at a lower Reynolds number.
I'm Kiefer Holcomb, and I'm going to be talking about permeable pavement, which is the application of flow through porous media. So cities display a remarkable transformation of the landscape from natural to human-made, and one of the most significant changes that comes with urbanization is impervious cover, which is the artificial structures that don't absorb rainfall. So that includes roadways, sidewalks, parking lots, stuff like that. And the water has to go somewhere. So usually it washes off into creeks and increases the magnitude of floods and pollution. And it also means that less water goes into recharging the groundwater resources, which was there before urbanization occurred. So what is the potential solution here? Permeable pavement. And here's an example of what it looks like. So pavement consists of three things: concrete, rock, and sand. And permeable pavement can be made just by leaving out the sand portion. And here's how it works on the scale of fluid mechanics. So here's a friction term. This is our Ergun equation for porous media. And then here's a simplified Bernoulli's. I chose 0.1 as the free surface standing water on top of pavement, so we can assume that the velocity is 0. And then the pressure terms are just going to be canceling out for simplicity's sake. If we plug in just a turbulent term of the Ergun equation down here, just for simplicity's sake again, and then solve for velocity, we'll find that there are some interesting things going on here. First, as you can see, the bed porosity E here, as bed porosity increases, the velocity also increases. And that makes sense. If you think about pavement, it has a very low porosity, if not 0. And so as you increase it to, leaving out the sand, the porosity is going to increase, and that'll let more flow through the pavement. Also, the diameter of the particles right here, leaving out the sand is going to result in an average increase in the diameter particle for that bed, which means that more water or any fluid is going to be able to flow through that. So those are some two really cool things to look at in there. All right, thank you.
Hello, my name is Ashley Chesney, and today I'm going to be talking about internal flow. So the first thing I want to note when discussing internal flow is the extended Bernoulli equation, which is the same as the simplified Bernoulli equation, except instead of setting the change in energy equal to 0, it is instead set equal to the work minus the friction. So the extended Bernoulli includes work and friction terms, whereas simplified does not. And in order to calculate the friction term, the Reynolds number must first be calculated. And the Reynolds number is the density of the fluid multiplied by the diameter of whatever the fluid's flowing through, times the velocity of the fluid, and then divided by the viscosity of the fluid. And using the Reynolds number, flow can either be categorized as laminar or turbulent. So if the Reynolds number is less than 2,300, then the flow is considered to be laminar. And if the flow is greater than 4,000, then it's considered to be turbulent flow. And if the flow is between 2,300 and 4,000, then it's considered to be in a transition phase. To calculate the friction factor, you first must multiply 4 by the Franning friction factor, which is F prime, and we'll go into that a little bit more in a second, and then multiply that by the distance that the fluid travels, so that can be either horizontal or vertical distance. Divide that by the diameter, and then multiply that by the velocity squared and divide by 2. For laminar flow, the Fanning friction factor is 16 divided by the Reynolds number. And for turbulent flow, the Fanning friction factor is this longer equation. And the key things to point out in this equation are this epsilon term, which is the roughness, and that's determined by the material of whatever the fluid is flowing through. So these values can be located in handout 12 for common pipe materials. The diameter of the pipe or the thing that the fluid's flowing through, and then the Reynolds number. Another way to calculate the friction term is by summing the loss coefficients of the pipe that the fluid is flowing through, and then multiplying this by v squared over 2. And this should give the same number as the friction factor shown right here, but is just another way to calculate that in a different scenario. So the loss coefficients can be looked at based on the differences in pipes in sort of the turns and entrances and exits that are present. And there's many different characteristics of pipes, but I'll just go over 3 common ones that you'll see and how they come into play when determining the sum of the loss coefficients in order to calculate the friction factor. So here's just an example of a pipe that has both bends in entrances and exits. So this is what you would call a sharp-edged entrance. These two things right here, this is a 90-degree smooth bend, and then this is also a 90-degree smooth bend, and then this is a sharp-edged exit. And each of these things have their own loss coefficient. So for a flanged 90-degree smooth bend, it will have a loss coefficient of 0.3, and for threaded, it'll have 0.9. And then for a sharp edge exit, in laminar flow, the loss coefficient is 2, and turbulent, the loss coefficient is 1.05. And then for a sharp edge entrance, the loss coefficient is 0.5. So if we were to assume that the flow was turbulent and flanged bends were present for the 90-degree smooth bends, then the sum of the loss coefficients would be the number of each of these components present. So for the smooth bends, it would be 2 times the loss coefficient 0.3. And then the exit, which had a loss coefficient of 1.05, and then the entrance, which was 0.5. And all of this added up to a total K of 2.15. And this loss coefficient could then be multiplied by the velocity and divided by 2, as shown here, and used to determine the friction factor. And all of these loss coefficients can be found in handout 3.